Dobrodošli u Veliku priču, još jedan uspešni podcast u produkciji Velike priče nedeljnika i studija u kojem razgovaramo sa najzanimljivijim, najuspešnijim ljudima iz sveta u poljima u kojima oni briljiraju. Danas imamo veliko zadovoljstvo, veliku ekskluzivnu priliku da razgovaramo sa Danom Adamsom, čovekom koji je glavni istraživač u kompaniji Neuralink i to je kompanija koja želi da od svih nas napravi robote, o čemu ćemo pričati ovom prilikom, i sa kojim ćemo razgovarati o onome što očekuje ne samo njegovu kompaniju, ne samo nauku i medicinu, nego možda čak i ljudsku rasu u budućnosti. I was just saying that you're behind a company that's trying to make the robots out of us all. Just kidding, but Mr. Adams, thank you for this opportunity. Thank you for your time. We wanted to talk to you first and foremost about the work that you do at Neuralink and the impact that it can have on the future of science, technology, human health, of course. But first I wanted to ask you about your trajectory and how you came to Neuralink. And I know that you've been an ophthalmologist, something like that. Yeah. You're interested in human vision. Yes. You're interested what drove you to this field?
So originally I was in academic neuroscience. So I was always interested in the brain. I developed an interest in the brain after working in a psychiatric hospital before I went to university. And so I studied neuroscience at University College London. And during that course, I became interested in the visual system. So the visual system in neuroscience is one of the best understood neural systems. And it happened that a professor at UCL, Professor Semir Zeki, was one of the preeminent scientists in the field of visual neuroscience. So I joined his lab to do a PhD. And following my PhD, I did the next thing, which is normal for a PhD student, which is to do a postdoc. So after a brief few months in doing some work in Japan for another visual neuroscience lab, I went to San Francisco, to UCSF, and joined a lab looking at binocular vision and how it develops and how that development can go wrong in a disease called strabismus, where the eyes can be crossed. And so I was very interested in how the brain deals with the fact that the eyes are misaligned. And so ordinarily this would cause double vision, but in someone who's grown up with misaligned eyes, the brain has a way to recalibrate and to cancel one of the images and to recalibrate the whole motor system. And so I was interested in studying that.
Just how complex is the human eye and the visual system? And what is it that we still don't know about it? You mentioned that we do know a lot.
Yeah, so the visual system is probably one of the best understood systems because it's easy to study. And one of the ways to study it is to record from neurons in the visual system whilst you present visual stimuli on a screen. And you can do this in non-human primates, in monkeys. They're trained to play video games by looking at things on a screen or press buttons. And you can then record exactly how their brain is analyzing that visual information. And so this was something that I set up at UCSF in a lab, and we recorded and looked at the anatomy and studied how the neural connections change in strabismus and how the activity of neurons is adapted to that misalignment of the eyes. And it was a fascinating process. We developed a much better understanding of how that double vision is mapped onto the visual cortex. And after a while, I always found that the part of neuroscience that I enjoyed most wasn't the actual discovery and the knowledge, but it was actually solving the practical problems and doing the experiments.
More of a technology than...
Yeah, exactly. Yeah. So, but your question, what don't we understand and what do we understand about the visual system? We actually have a very good understanding. My PhD supervisor, Semir Zeki, was one of the first people to discover that the visual image is separated into different sort of streams functionally in the cortex, and each area that visual information is sent to processes a different attribute of vision. So there's an area specialized for processing motion vision, for example, another area that looks at form vision. And so that kind of basic mechanistic segregation and neuroanatomy is very well understood. And there's a lot known about how neurons represent oriented lines, for example, or colors, using center surround organization. And so on a mechanistic level, it's very well understood. The part that's missing is how all of that neural machinery integrates together to produce what you and I see in front of our face.
Consciousness and perception.
Perception.
Yeah.
We see this beautiful image that is perfectly stabilized and in full color and depth. And I think what many people take for granted is to think that reality is really like this. But in fact, color is just a tiny segment of the electromagnetic spectrum. There's no color in the real world. The reason we see color is only because we have 3 different cone receptors in our retinas. And depth, for example, depth is a mathematical process that is reproduced by the way that our brain compares the image between our 2 eyes. So it looks at the small differences in each image that are caused by the fact that the eyes are horizontally separated, and calculates the depths of things and superimposes that onto our image of the world. So what we see is really a reconstruction of the world. It's not reality as such. And so I think what's missing in our knowledge is how all of those pieces of information, depth, wavelengths of light, motion, and everything else is put together into our percept.
Was it that sense of wonder that actually made you join Neuralink?
Partly. I think what really made me join, honestly, what made me join Neuralink is that I saw, as I was saying before, the part of science that I always relished and got the most reward from was actually the craft of science, not the sort of academic pursuit. Of course, it's wonderful to discover things, and I was fortunate enough in my scientific career to sometimes even serendipitously discover things about the brain. But what I enjoyed most was building the equipment, doing the experiments, working with my hands, and producing something tractable that I could, that was more than just a manuscript. I think, the major output of a scientific lab is a manuscript. I felt I needed to produce something more tractable. And what drew me to Neuralink was the opportunity to use all the skills that I'd developed in my scientific career to produce something that, firstly, I could actually hold, and secondly, that actually could have potentially a very substantial impact on the world.
How would you sum up the mission of the company?
The mission can be summed up in different ways by different people. For me, the mission is to use the knowledge that has been developed over the last 20 years in science to produce a product that can help potentially thousands or tens or even millions of people. Much of what we do at Neuralink is not science. What we're really doing is developing the technology to put a scientific discovery into the world in a realistic way. The things that we've been working on have been around for 20 years. For example, the motor BCI, a system where you can record from the motor cortex of the brain and convert that into motions of a mouse cursor on a screen. This is nothing new. What our mission is to take that science and make it into something that can actually help people. Scientists always say, we're working on this because one day we can help thousands of people with it. Well, that day has come. And that's what we're doing. We're converting science into a therapeutic product that people can use, take home, and just use from day one. I
think the first product that actually made the headlines was when Noland Arbo, was it?
Yes.
If that's his name, he received a brain implant so he could,
yeah.
And the paralyzed people could move around and move the cursors around. So can you tell us a bit about Nolan's life and how he's been doing, and what are some of the other patients or some of the trialists?
Yes. So yeah, Noland, we call Noland P1 for participant 1, had his implantation surgery just over a year ago. It was February, I think, of 2024. And from the very first day of turning on the device and calibrating it, he was able to move the cursor on the screen. I think even in the first 24 hours of recording, he shattered the world record for speed and efficiency in moving a cursor using just his mind. And since then, he's basically been able to use the device at his home. So he went home after the surgery. And one of the things that we thought was very important and distinguished us from the research labs that have been working on this technology is that we always wanted this to be something that a person would be able to get a benefit from day one. So the beauty of our device is that it doesn't require banks of amplifiers and equipment. It's completely subcutaneous, so there's no connector or anything that has to be handled by anyone else. The participant can simply turn on the device, charge it themselves with a magnetic charger, and actually use it. And Noland is, to this day, still using his implant for as many as like 10 hours a day. Recently, he went on a 72-hour-long session where he streamed himself on X, playing video games, playing chess, and just to see just how long he could use his device for. So he's doing fantastically. In fact, we could not have chosen a better person for our first participant. He's incredibly hardworking and driven, and is just a really wonderful, inspirational guy.
Can you tell us a bit more about the process of implanting?
Yeah.
And how does the chip work, and what does it look like, and how do you install it?
Yes. So as far as neurosurgeries go, it's probably the least neuro of surgeries. So I make jokes with the surgeon that if the neurosurgeon doesn't actually touch the brain, then this is an optimal surgery. So the role
is he a surgeon then?
Well, it's arguable. So the role of the surgeon. It's a standard. And we've teamed with a group at the Barrow Neurological Institute, and the surgery is we make an incision in the skull, probably about the shape of your hand, like this, and peel back the scalp, and we drill a perfectly round hole that's about 25 millimeters in diameter. And that exposes a layer underneath the skull called the dura. And the dura, then we cut a little circle around the dura and remove a disc of dura, and that exposes the brain surface. And at that point, the neurosurgeon's job is done, apart from afterwards, to put everything back together. So at that point, the surgical robot steps in. The neurosurgeon arranges the participant's head underneath the robot, and the role of the robot is to insert the electrodes. So the electrodes we use are incredibly fine, much finer than human hair, just order of 20 to 25 microns wide, which means, and they're incredibly flexible as well. They're so small that if you hold one and let go of it, it just kind of floats away. They're ephemeral, and so that means they can't be inserted by hand. They have to be put in with a needle, and of course, being so fine, and no human hand would be steady enough to put them in. So that part of the surgery is done with a robot. The robot is essentially, you can think of it as a giant sewing machine. The needle on the robot, unlike a normal sewing needle, the loop is actually on the end of the electrode, not on the needle. But the needle picks up a single electrode, or a thread as we call them, and transports it over to the surface of the brain, and avoiding the surface vessels on the surface of the brain, pushes it in to about 3 or 4 millimeters. And each device has either 64 or 128 individual threads, and the robot just repeats this process until all of those threads are in the cortex. At this point, the robot's job is done, and the neurosurgeon steps back in, and the device, actually, I can show you. Here's the device. It has a round base and a sort of mushroom top, and the base is exactly the same diameter as the hole, so that basically fills the hole.
It's a bit heavier than I expected.
Fills the hole that the surgeon cut in the. So this basically replaces the skull, and all of the device is mostly in the place of the skull. So it sticks up very little. You can't really feel it through the scalp, and it's just held in place with 4 little screws. At which point the scalp is sutured over the top, and after that, there's no, apart from the scar, which heals very quickly, there's no sign that the device is.
So, like you said, no wires or nothing like that.
There's no cables or wires or anything. All that's left is a little, just a normal sort of horseshoe-shaped scar in the.
You don't even have to plug yourself in.
So the only thing that it requires, there is a battery, and which means it has to be charged. It's just a standard lithium-ion battery, and it's charged with just like your toothbrush. It's charged with a magnetic coil, and that has to be held quite close to.
So it looks like a Bluetooth speaker, something like that.
So exactly. So when it's charged, it advertises as a Bluetooth device.
So you can connect with.
And it's connected just as you would connect your computer to a Bluetooth mouse. So in fact, you can think of it basically as a Bluetooth mouse in your head. So you go next to a computer, the computer says, I detect a Bluetooth device, you pair it, and we have some special software on a computer, but it's just a standard Mac computer. And then at that point, the person can move the cursor on the screen without having to move.
So where does your research come in? Like, what can it do with the visual information?
Yes. So for that application, the device only needs to record from the brain. It's placed, the electrodes are placed into the part of the cortex that would ordinarily control the hand and the arm. So even though those neurons are still active when the person volitionally wants to move their hand, the signal never gets to the muscles because the spinal cord is cut. And so what the device does is record those signals and convert them into XY movements of a mouse on the screen and a click signal. To reproduce vision or to generate visual perception, we need to do more than just record. We need to actually stimulate. So the same types of electrodes and the same device can actually push current out of those electrodes, and instead of recording activity from neurons, it can generate activity in those neurons. And when you do that in the visual cortex, you cause the perception of a small dot. And the visual cortex is organized rather like the retina. So you can think of the visual cortex like a sort of TV screen inside your head. So whatever you perceive is actually reflected in a retinotopic way on this small piece of cortex that's about the size of a credit card in the back of the brain. And so neighboring points on that sheet of tissue represent neighboring points in the visual world. So if you stimulate, you can actually produce a pattern of dots perceptually, they're called phosphines. And then if you stimulate with patterns, you can actually generate features and lines that correspond to stimulation of the retina.
So a damaged eye could hopefully be able to project something inside the brain.
Yeah, so the eye can be even missing altogether. Yeah. So there's a group, again, we're not the first people to do this. There's a group headed by Eduardo Fernandez in Velike in Spain who have a device similar to ours implanted in a person who lost both eyes in a bomb explosion. And so he has no eyes at all, yet he can perceive points of light from the stimulation device in the occipital cortex.
So, for example, can the system in the near future, recognize faces also, so that the person might know, who is technically blind, might actually realize that, you know, my wife has come into the room, or right, my daughter has come into the room.
Yeah.
Is it something that you're working on?
That's something that we're working on. So I don't want to overstate the fidelity that a device like this can have. We're basically going to be working with a small, by small I mean maybe 2,000 to 3,000 points of light scattered over probably a range of maybe 20 degrees of visual field, so a 20-degree angle from the fovea. And with that kind of fidelity of vision, it's going to be difficult to make out fine features. It's going to be difficult to read text or to see. If you imagine like looking through, imagine your vision is like a dot matrix printer, but very coarse. But what we can do is we can do what I like to refer to as off-brain processing. So we can take the image from a camera that could be mounted on a person's glasses, and that image will have to be analyzed to produce and turned into a pattern of stimulation of the electrodes. But at that point, we can also do clever things in software like image segmentation. We can do things like face recognition, online face recognition, and then you could actually communicate to the person not by their visual perception, but by other means. For example, you could have certain dots that signal different features of the world. So let's say your mother walks in the room and she's recognized by the computing device, and then you have a particular phosphene that lights up to say, oh, this person is your mother. So, and there are very many things that you can then actually exploit in terms of image processing and analysis that you wouldn't be able to do with such a coarse representation of the world from the device alone. Things like navigation. You could have phosphenes that tell you which direction to walk, or you could also have phosphenes that are active in different kinds of situations. So, for example, you could switch a mode to sidewalk mode, where it doesn't show you things that you're not interested in, but it will show you where the edge of the curb is, and it will show you lampposts that are coming and things like this. Yeah. It won't show you like a bird or writing on a wall or something, but it'll just show you the important parts of the visual field. So I like to refer to it more as a visual aid rather than restoring vision, because when people think about vision, the first thing they imagine is this fantastic, multicolored, almost infinite resolution miracle that we all have in front of our face. And unfortunately, we're not able to approach that yet. And for me, coming from a scientific background, it's hard for me to imagine ever being able to reproduce the kind of fidelity and the kind of beauty that we have in normal vision. But what we can do and what we hope to do is to produce something that is useful. And so far, that's actually been a big challenge.
Have you already recruited some patients?
So we have an online registry where people can register. We don't yet have approval from the FDA to do a human clinical study. We're hoping to get that soon, and so we haven't recruited anyone until we get to that stage.
So I have to ask you about some ethical issues concerning this technology, because I think, as is the case with every technology, there are going to be some people that are concerned with ethics. What would you say to the detractors, to people that are worried that this is, playing God or opening Pandora's box or something like that?
I think we have to think about the brain just like we think about any other organ. We have an opportunity to address a great many debilitating diseases. And I think we also have the next, I don't know how long before the end of civilization, hopefully a few thousand years. I mean, humans on this planet we're in our infancy. Technology has developed, I would say, incredibly quickly, but it's developed at the rate it's developed, and it'll continue developing quickly. So I think it's inevitable that we will find ways to cure problems with the brain, just as we have for other organs. And in terms of ethics, I think that I'm an atheist, so playing God to me is a little bit of anathema, but I think we could level the same criticism at medicine throughout history. People have always said, oh, you shouldn't be interfering with biology, this is how things were meant to be. But actually, when it comes to alleviating suffering and increasing well-being of humanity, I don't see an ethical issue. And of course, every technology can be used for good or bad. This is clearly true. Look at history, but that should not prevent us. I mean, that shouldn't make us sit on our hands and not do things that we're capable of doing. I think that's it's almost impossible when you think about the next 100,000 years. This is always going to be a taboo subject, or we're stopping ourselves from doing this because of a perceived ethical concern. The ethics surrounds how it's used and not the technology itself.
I think one of the topics that is connected to this very question is the rise of artificial intelligence. And in your field of work, how does it help you, this new technology that everyone is talking about?
On a day-to-day, well, by artificial intelligence, I assume you mean like a large language model type. Yeah. So how that helps us is, well, how it helps me is it makes me a better programmer. It helps with writing documents and things. The large language model is really a way of condensing information or searching for information. It's just a fabulous search engine. So now, you know, you can ask very specific questions, and the large language model has the entire internet at its disposal to summarize and to put things together. In terms of actually using that in the technology, is actually it's not really used in our technology. What is used is very basic neural networks and machine learning. And those are used primarily for the algorithm that converts the neural activity into an XY signal or the movement of a robotic arm or all those sorts of things. So that's really a mechanism, like a mechanistic algorithm-based system. But the large language model is I mean, it's extraordinary, but it's not really an engineering tool.
So let me take you back to Neuralink once again. What does the environment of the company look like? You know, you have these vast resources and you have these scientists and technologists, and do you get along?
Yes. Is
there competition with, you know, if that doesn't work, you can always like turn on the cameras and everyone's going to watch it like a documentary.
It's a fantastic environment. It's I think because we're at the forefront of technology on many different levels, and so the device has a whole range of different kinds of technologies. We use thin layer production for the threads, so we have a full silicon wafer production fab. So we have the world's best experts on lithography and producing those kinds of electrodes with different layers, and we have custom designed chips. So we have ASIC designers. We have a whole range of mechanical engineers. So we build the robot, the implantation robot as well. And so we have mechanical, electrical engineers. We have chemical engineers for looking at the electrochemistry of the threads and recording and stimulation. And so we have experts from so many different fields of engineering and technology. In fact, and me, you know, I'm not an engineer, but my father was an engineer, and I've always kind of felt like I should be an engineer. So I'm a neuroscientist, and I think the one thing that is probably least required is my role in the company. Scientists in general publish everything they know. That's their purpose. So why do you need a scientist and the company if you can just go and read their papers? And as I say, we're not actually doing scientific research. What we do looks very much like scientific research. You know, we have a lab, we have equipment, we have microscopes and amplifiers and everything else, but we're not really doing science. So I often joke that my role is just to have good lunchtime conversation.
And speaking of which, since you're around so much wisdom, can you perhaps tell us about some, breakthroughs that are coming in science? You know, what is around the corner and what is still a moonshot?
Well, advances or breakthroughs in science often are caused by breakthroughs in technology. And so, you know, in my field, in visual neuroscience, the real genesis of visual neuroscience came with the development of recording electrodes. And so, and the techniques for recording in animals whilst they were doing visual tasks. And you can in almost every field, for example, you can see the invention of a new technology and then the huge spike in knowledge generated. So, for example, fMRI was a technology that arrived in the 1990s, and suddenly the academic literature was filled with new discoveries in fMRI. So when you think about what's the next big thing in science, you have to think about what's the next big thing in technology. Yeah. And there are one of the nice things about Neuralink is that we've sort of started a little revolution in neurotechnology. So lots of companies are now looking at ways to stimulate and to record from the brain. And so I think that the boom in technology caused by neurotech will inevitably cause a peak in discoveries about the brain. So for example, you know, one of the great things about the Neuralink device is that now we can record from thousands of neurons in a person just as they walk about, or as they can't walk because they're paralyzed, but as they go about their daily life. And this is something that has never been possible until now. So it's almost inevitable that those discoveries will be made given this new source of data. And we also have, so to test the device, we've also implanted a number of monkeys in the lab. So we've collaborated with some academic groups who will come in and record from the monkeys as they're running around and chasing each other inside their cage and playing with toys and things, and you can film them, and then you can also have an online readout of exactly how the neurons in the brain are firing. And again, this, even in academia, this is something that, for me as a neuroscientist in the field, has always been a dream, that you would be able to record from neurons in a totally unrestrained, normal animal, just as it's running around doing its normal things.
That sounds hopeful for the primates and for the monkeys and for the people too.
It's, you know, it's a great technology, and it really needs to be put into the hands of scientists. Yeah,
like you said, if it's used for good, then it's a good thing. So, Professor, thank you for your time. This has been wonderful, I think, and really insightful.
It's been a pleasure.
Thank you, and best of luck with your work.
Thanks very much.